Hi, this is the third installment in a series of 3 videos on DNA replication. In this video, I'm going to be covering lagging strand replication and how it involves Okazaki fragments. I'll also be talking about DNA polymerase I and ligase and the role that they play in making the lagging strand into one continuous piece. Then we'll turn our attention to how you can draw this and represent this for your task. And then finally, we'll look at a diagram that incorporates both leading and lagging strand replication and kind of pulls everything together. Okay, so replication on the lagging strand is challenging because the replication fork is moving in this direction. So as we said, this is the direction that helicase is moving to unwind the parental strands of DNA. But polymerase III is building strands in the opposite direction, moving away from the replication fork. So what this means is that the lagging strand is actually going to be synthesized in fragments. And right here in maroon, I've shown a primer, and the 5' end of that primer is here. DNA polymerase III is going to latch onto the 3' end of that primer, and it's going to add nucleotides. Again, it's progressing away from the replication fork. It can't get too far away from the replication fork, however, because all of the machinery that's involved in DNA replication sort of remains at that fork. So when it gets a little too far, it jumps back, and it's going to find another primer and start this process moving away from the fork again. And so what we end up with is a situation where the lagging strand is made in these Okazaki fragments. So it will make one fragment, polymerase III will make one fragment, and then again it has to stay close to the replication fork, so it jumps back, makes another fragment. As it gets too far away from the fork, it will jump back, and this keeps happening. And ultimately, those fragments need to be pieced together. And so the primers are going to need to be removed, and also then the 2 fragments are going to have to be put back together. So here, I've illustrated 2 Okazaki fragments. I'm going to call this Okazaki fragment A. And I'm going to call this second Okazaki fragment B. Okay, so removing the primer and joining Okazaki fragments involves a couple of different enzymes. The first enzyme is DNA polymerase I. Its job is to remove the primer and replace the primer with DNA. And it does so by grabbing onto the 3' end of Okazaki fragment A, and polymerase I is going to add DNA nucleotides onto the 3' end of fragment A while it is removing the primer of fragment B. Once it removes that fragment, that primer, it can't form the bond that links the 2 fragments together. And so that's the role of DNA ligase. So ligase is going to come in and link fragment A and fragment B together. And now we have one continuous piece of DNA. Okay, so how can you represent this for your task? Well, once again, I think it's good to represent the DNA very simply, just by using lines. And you'll want to make sure that you label the 5' and 3' ends of your DNA strands. Okay, so for lagging strand synthesis, I think it's good to show that this occurs in stages. And the fragments that are at their very earliest stage of synthesis are going to be closer to the fork. Those that are more mature are going to be out further away from the replication fork. And the first step in Okazaki fragment synthesis is the addition of an RNA primer. And again, that involves an enzyme called primase. So we're going to represent primase with a red circle. And then the primer that it makes is shown with the red line. So that's our RNA primer. In the second step of Okazaki fragment synthesis, the primer will already be there. And at this point, DNA polymerase 3 is going to latch on, and it is going to add DNA to the 3' end of that primer. So our DNA polymerase 3 is shown with the blue circle. Okay. In the third stage of Okazaki fragment synthesis, this is going to be where primers end up getting removed. And you're actually going to have to show multiple Okazaki fragments to show this clearly. So I'm drawing a couple of different fragments here. And DNA polymerase 1 is going to grab onto the end of Okazaki fragment. We'll call this fragment A. And this is fragment B. So DNA pol 1, it grabs onto the 3' end of fragment A, and then it's going to sort of bulldoze through the primer of fragment B, and it removes it. So this is DNA polymerase 1. And because DNA polymerase 1, it's adding on to the 3' end of the DNA of fragment A while removing a primer, you need to make sure that it's placed between a small segment of DNA and a small segment of RNA. Okay. And then finally, in the fourth stage, this is where ligase is going to come into play. I will represent ligase with a rectangle, a red rectangle, and its job is going to be to join the Okazaki fragments together to make one continuous piece. And all of my enzymes, I want to make sure that I'm showing my enzymes in a key so that the evaluator knows what these symbols stand for. Okay, so that's a pretty good representation of lagging strand synthesis. Okay, so ultimately you're going to need to kind of put things together showing both leading and lagging strand replication. And this is a really nice diagram from Campbell Biology that shows leading strand synthesis here at the top and the steps of lagging strand synthesis here at the bottom. And one good exercise would be to pause the video at this point and see if you can label the enzymes that are labeled A through F. The answers to those are at the very end of this video, so you can check your answers when you get there. Okay, and when you make your diagram, you're going to want to make sure that you include all of the components on this checklist. If you miss one of them, it may be enough reason for your test to come back, so you want to be thorough and just double check that you've got all of the items shown on this list in your diagram for the task. All right, I hope this video was helpful. WGU students, feel free to contact us at biochemistry@wgu.edu.